Deletion in binary search trees can be a bit tricky. We break it down into three cases: deleting leaf node, node with one child, and node with two children. Before we go into three cases, note that after delete, the ordering property of binary search tree should still be preserved. Deleting leaf node is very simple. Just remove the node from its parent. For node with one child, we can promote the child to its position by linking its parent directly to the child. Is this still in binary search tree? Yes, because the left child is smaller than the deleted node, therefore also smaller than its parent. The last and most complex case is when the node has two children. Let's take node 5 as an example. We can't just promote one child because both children can possibly have two children, like node 10. If we promote node 10, then we don't have place for node 3. One working approach is that instead of removing the node, we replace its value with the smallest element in right subtree. Then delete that smallest node. So why does this work? According to property of binary search trees, any node in right subtree is greater than node itself, which is greater than any node in left subtree. So the smallest element in right subtree is still larger than any nodes in left subtree, while being smaller than rest of nodes in right subtree. So ordering properties still hold. Now, how do we find the smallest element in the right subtree? Remember that left child is smaller than its parent, so we'll start from root of right subtree, then follow left edges as much as possible. When reaching a node without a left child, then it's the smallest node in subtree. This is also what happens during in-order traversal. Remember that in-order traversal of binary search tree effectively sorts all nodes from smallest to largest. This next large value is usually called the in-order successor of the node. Now, back to the deletion process. After we replace the value of deleted node, the last step is to delete the in-order successor. Because it either is a leaf node or has one right child, this deletion reduces to the two cases we mentioned earlier. Let's look at another example by deleting node 10. In this example, root of right subtree doesn't have a left child. We have no left edge to follow. So root node 11 is the smallest node in right subtree. Now let's look at the code. This is a recursive implementation, and here's a summary on what it does. If the current node is not the node to delete, pass down delete operation to its left or right child. Notice that the return value is assigned to the child. We'll mention this later. If it is the node to delete, handle it according to the three cases. Notice in line 24, we have a helper function find subtree min, which, like mentioned earlier, follows left edge as much as possible to find the minimum value. The return value is the updated node at current node's position after deletion is done. Once the function returns, this value is used to update at parent level at line 6 and 8. For leaf node and single child node, this is how it's removed from tree structure. For the case of two children, function returns the same node object, but the number at this node has been changed. Finally, there's the base case. This if check can be true under two conditions, when value to delete doesn't exist, or in two children case, successor doesn't have a right child.